All right, physicists, welcome to our April 9th edition of physics. This week we didn't have a lot of time to do new stuff because we only met on Wednesday, but we did cover a very important thing. So if you don't cover a lot, you've got to do something important. And the important thing that we covered was Newton's law of universal gravitation. As I say, if you remember two equations from this course, this is a good one. And the other one that's really good is Newton's law of gravitation. M1, M2 over r squared. And it's in the r hat direction. I'm going to take this off and not make it a vector equation. Okay, so those are my two favorite equations from this course. And it's because they're both very general and very helpful. And we used this to derive Kepler's law of periods. So the amount of time it takes an orbiting object to go around the Earth depends on the mass of the Earth and how far away from the Earth it is. So for instance, a satellite that's up here will take longer than a satellite that's further, that's nearer to the surface. Okay, so those are our two big ideas. Remember, the reason why this was a big revolution in thought and even your humanities professors might get excited about this one, is that this was part of the scientific revolution and the Copernican revolution, where it was discovered, reframed, something like that, that the stuff up in the sky is approximately is part of the same system that the stuff down here, all part of the same system as opposed to being two separate types of realms. Okay, so I put a couple questions here at the beginning to remind us we have a quiz today. Okay, which one of the statements concerning Kepler's law of orbits is true? All planets move in elliptical orbits with the sun at one focus. I agree with that. Let's not go farther. Okay, so what is an ellipse? An ellipse is if you have this plus this, that and make a string there and put a thumbtack in each one of the foci and then draw a line around on the piece of paper, keeping that piece of string taut everywhere. You'll draw out a shape. Okay, and if those two foci are right next to each other in the center, this becomes a circle. So Kepler's law of orbits works for elliptical orbits and for circular orbits. And this preceded Newton, so Newton was able to use this idea to, I'm not going to say he derived the law of universal gravitation from it, but it's something close to that. So here's a more pressing quiz question. I have one on the quiz that's similar to this, not the same. And it says, two objects with masses m and big M are separated by a distance d. Okay, so I have m and m at a distance d. What would the gravitational force be for that? Well, it would just be g, which is a constant number. So that's your 6.67 times 10 to the minus 11th. Kilograms or newtons times meters squared over kilograms squared. Okay, really weird units that are cooked up just to make this whole thing have units of force. Okay, so in this case it would be G m over d squared. That would be our force. And keep in mind, because of Newton's third law, the force of big M on little m, this force, is the same as the force of little m on big M, that force. So Newton's third law says these two forces are the same. However, the little mass will be more will experience more acceleration as a result. Okay. Now it says, if the distance between these objects is increased to 4d, okay, so they spread out. Here's my m, there's my big M, and now instead of this being a distance of d, this is a distance of 4d. Well, in that case, the force of gravity would be gmm over 4d squared. So this would be 1 over 4 gets squared, d gets squared, 4 squared is 16, gmm over d squared. Okay, so this is 1/16 of that, and that's our answer. Okay. All right, now I have to admit to you, most of the quiz is not gravity. There's only like one question out of it on this new gravitational stuff, because I want you to have a chance just to review some of the angular dynamics that we've been studying so far. So let's take a look at this one. It says the entrance door to a video store is pivoted about the hinges on the left side of the door. Okay, so let me draw this door. Here's the left side, here's the right side, there's the hinge. Okay, so this is your axis of rotation of the door. If I look at this from above, it's going to look like this. There's my hinge. Left, right. Okay, so it says, when you begin to push the right side of the door to enter the store. Okay, so I'm going to push in. So F is going into the page. The usual physics way that you draw that is with a little circle and an X. In this note, the idea behind this notation is that you're imagining a arrow and the feathers at the back make an X. That's that's the idea. Okay, so there's a X. It's going into the page. If I'm looking at this from the top now, there's my force going like this, and it asks, when you begin to push the right side of the door to enter the store, what is the direction of the torque on the door? Okay, so the torque is pushing this way. You have to use now your right-hand rule. So you go R cross F gives you your torque. So in this case, I would draw my torque as being in that direction. Okay, so this is my direction of my R from your axis of rotation to the force. Your force is into the door, into the screen, and torque is up. In this picture, it would be R cross F. So this is my R. This is my F. And in this picture, the torque would be coming out of the page. Okay, in our arrow notation, that little dot is supposed to be the tip of the arrow. I know, it's a little goofy. Okay, so anyway, it would be upward. Okay, so I'll give you a problem like this on the quiz. In the problem on the quiz, you do need to be careful to think about this angle too. So the angle that you're worried about is like this angle. In this one, it's just 90 degrees, so sine of 90 would be 1. But if it's an angle smaller than that, the torque can also be diminished. Whoops. Okay, and I think I gave you this one already, but it doesn't hurt for us to review it again. If we have north, east, south, and west, it says a hoop rolls without slipping on a horizontal surface as it moves due east at a constant linear speed. What's the direction of its angular momentum? Well, this one is another one for your wheel is going like this, and you need to take your hand and go and curl it around like this, and then your thumb is going to be pointing north. Okay, so the rolling is like this, and then this would be your direction of your angular momentum, be pointing north. Okay. This is a question that I think is good just to think about a little bit. It says you've got two identical cylinders, and they're both going down a ramp like this. And I believe you did something like this with Dr. Galaba in lab this week. So here's cylinder A and cylinder B. Cylinder A is allowed to roll down a ramp without slipping. Cylinder B is allowed to slide. So this has friction. This has no friction. Which one of the following statements concerning this situation, assuming the cylinders begin from rest at the same height, is true? So the thing is, when you have friction at the bottom of this, right here, A will be rolling, and as it rolls, it moves down. So if you wanted to find the kinetic energy of A, it would be equal to Ka rolling plus Ka translational, right? On the other hand, this one is just smoothly falling down the ramp. It's not getting any spin going. So Kb is just Kb translational. Okay, it's not spinning. It's just sliding. Now, in each of these cases, they start out with some mgh. mgh. That's your gravitational potential energy, and that gravitational potential energy is transformed into this energy of rolling and translation, or just rolling. And so in both cases, the total amount of energy is the same because it's just transferred from one medium to the other, but the difference is that in the case of B, it's simply translational kinetic energy, and it's not rolling. Okay, so today I brought out the old spinning devices again, just because I like the demo. It's cute. I think it's a little fun. And it says, what happens when a spinning ice skater draws in her outstretched arms? Well, your moment of inertia is the sum of all your masses times the distance to the axis of rotation squared for those masses. So what happens essentially is she pulls in her arms. The mass of her arms are now closer to her axis of rotation. So the I omega at the beginning is the same as the I omega at the end, but this has gone down. The moment of inertia has gone down, so this has to go up for the product of the two to stay the same. So her moment of inertia decreases, causing her to speed up. Okay, so that's the sort of stuff you'll see on your quiz today. Now, today I just want to cover a couple new topics on gravitational stuff. Now, one of the things that I want us to think about today is we've been using 9.8 meters per second squared, or newtons per kilogram, as g. And g, we've been using it as gravitational acceleration or your gravitational field strength. And that all does connect up perfectly well with Newton's law of gravitation. So let's see how that works. The other thing that I'm going to talk about is gravitational potential energy being negative. Why that is probably it's not a question you asked unless you've taken this course already and you know that gravitational potential energy is negative. So I'm asking it as a question, but I'm also aware that it might not be a question that was at the forefront of your concerns until a moment ago when it came out of my mouth. And all right, and then the last part is, if you shoot a rocket up from the surface of a planet, how fast does it have to be going to escape the gravitational clutches of that planet? Okay, so just to make sure that we're rock solid steady on the stuff that we did on Wednesday, Here's a homework example. By the way, remember, homework due Monday. So you do have some work to do here. Okay, so we want to position a space probe along a line that extends directly towards the sun in order to monitor solar flares. Okay, so here's the Earth, here's the sun, and somewhere between there we're going to put some sort of a space probe, and it says how far from Earth's center is the point on the line where the sun's gravitational pull on the probe balances the Earth's pull. Okay, that's an interesting question. Now, the thing you might ask yourself, okay, should I expect this to be closer to the sun or closer to the Earth? Well, I would expect it to be closer to the Earth because the Earth has a smaller mass, and so its gravitational force is going to be lesser at an equivalent distance. So, all right, so we've got to get it closer so that these forces can be equal in size. So let's call this distance, this whole distance is what's called an astronomical unit. It's the distance from the Earth to the sun. And something to just notice in these questions is that there's sometimes data that is left out of the question that they expect you to look up. So for instance, in this one, you would just be expected to say, oh, how far is the Earth from the sun? I can look that up. So you have here RAU. Okay, so this is one astronomical unit. That's the distance from, average difference from the Earth to the sun. Now that doesn't give you this length or this length though, because this would be, well, let's just call that the radius to the Earth. And then this length right here would be RAU minus the radius to the Earth. Okay, now our claim is that we want to find out where the force of gravity from the Earth equals the force of gravity from the sun, pulling the other way. Okay, so when Fe equals F sun, what we have there is going to be, let's put a little piece of mass there. Here we've got the mass of the Earth, the mass of the sun, and you notice they've got a little bit of a fancier way with a cross and a dot, but let's just use E and S. Okay, so on this side we have G, little mass of my of my space probe, times mass of Earth over R Earth squared equals Gm mass of sun over, now this is going to be RAU minus RE squared. Okay? Now, if I want to simplify this a little bit, I can divide both sides by G. I can divide both sides by M. And let's then cross multiply, and I would get ME times RAU minus RE squared equals MS RE squared. Okay, then I could go ahead and FOIL this out. ME RAU squared minus 2 RAU RE plus RE squared. Wait, did I screw this up? No, I think we're okay. All right, and then I just need to get this in a form where I can solve for RE as using my Pythagorean theorem. Okay, so I'm going to, maybe the easiest way to see this right here is just to bring this over and go ahead and have ME minus ms RE squared. And then my next term would be minus 2R AU ME RE. And then my last term would be ME RE squared equals 0. Okay, so this is something where if I use this as my A, my B, whoops, and my C, I can use my quadratic formula and solve for RE. Okay, so you know it's a little tricky, but it's not too terrible. Similarly, here's a question. It says, what linear speed must an Earth satellite have to be in a circular orbit at an altitude of 160 kilometers above the Earth's surface? And then what is the period of revolution? Well, it seems to me like the second one of those is actually a little easier than the first. It says, what is the period of revolution? Well, if I'm given this equation that we derived last time, Kepler's law of periods, well, in that case, the R from the center of Earth that I care about then would be 6,378 kilometers, plus this extra bit above, which would be 160 kilometers. And then to make the units all play nicely, I might want to make this into a distance in meters. Okay, so that's your R, and once you have that R, you can go and look up what is the mass of the Earth. Well, the mass of the Earth is going to be 5.972 times 10 to the 24th. Kilograms, 5.972 times 10 to the 24th. Looks right. Okay, and once you have that, and G of course is just a number, right? That's that 6.67 times 10 to the minus 11th in some units, newtons, meters squared. Okay, so once you have all these numbers, it's easy to find your T because you can just plug all of that stuff in. So you have your 4 pi squared over GM R cubed, and you take the square root, and you get your amount of time. And so that'll be a time in seconds. And then if you wanted to find your V, it would just be 2 pi R, the total distance, over that total time. Okay, so that's a common type of problem. I will say this problem, to me, when I put it on the homework, it looked exactly like the last problem. But I realize if you're coming upon it for the first time, it might seem harder. In this one, it says you have the sun. Okay, is 2.2 times. Oh, the mass of the sun is 2 times 10 to the 30th kilograms. A big boy. And it is revolving around the center of the galaxy. So there's your UR here type of picture. And the distance is 2.2 times 10 to the 20th meters, and the time is 2.5 times 10 to the 8th years. And when I see a unit like that, I think to myself, okay, 1 year is 365.25 days, and then 1 day is going to be 24 hours times 60 minutes times 60 seconds. Okay, so you can change your t into seconds if you want to. Now it asks me to estimate the number of stars in the galaxy, but here's the way that I'm going to do it. I'm going to use this law of periods. Then you could go ahead and solve for the mass of the galaxy, the thing that that our solar system is revolving around. Okay, so just to rearrange this a little bit, it would be something like mass of the galaxy equals 4 pi squared over gt squared times r cubed. And then your number of stars is going to be approximately the mass of the galaxy divided by the mass of the sun. And you're assuming that the sun is kind of a normal-ish star, and then this would give us our number of stars. And so don't be freaked out when you get a big number, because galaxies are really big, and you'll get a big number. All right, so let's bring things down a little bit closer to home. Here we are on our cradle, the place of our birth. Our Earth radius is about 6.378 times 10 to the 6th meters. Earth's mass is somewhere around 5.9722 times 10 to the 24th kilograms. Now, let's suppose that we wanted to find G in terms of our F equals ma and our force of gravity from Newton's universal law of gravitation. Okay, all we would have to do is say this force is the thing that's causing my acceleration. So I would say ma equals g big M, that would be the mass of the Earth, times my little mass that's being accelerated, over r squared. And r squared is the distance between my center of mass of the Earth and this center of mass of the little mass. Okay, these little m's cancel out, and our acceleration that we would get would be gm over r squared. So that would be our gravitational acceleration. Now, a good exercise to make sure that you're sticking things into the calculator properly is to actually try this out. So this is your newtons times meters squared over kilograms squared. That's your G. Your M should be 5.972 times 10 to the 24th kilograms. And then your R squared is going to be 6.378 times 10 to the 6th meters, and you're going to square that. And so you take this number times this number divided by this number divided by this number again, and it should give you somewhere right around 9.8 meters per second squared. Okay, so you want to be able to get that out of your calculator. And if you can get that out of your calculator, thumbs up, good job. You are on your way to being able to do these types of problems. Otherwise, you might want to try to do a little troubleshooting to figure out where do you need to add extra parentheses in your expression. Okay, so I ask you a similar question to this. I ask, at what altitude above Earth's surface would the gravitational acceleration be 4.9 meters per second squared? Well, in our last one, we just said G is big G over m r squared. And so we're saying if you go up, the gravitational force on the Earth, from the Earth goes down, down, down. And so if you wanted to find what distance you would get a particular gravitational acceleration from the Earth, it would be gm over little g. And then we can take the square root of both sides. And there you go. So your R is going to give you some number. And if you wanted to just find the altitude, think about the Earth is down here. There's the surface of the Earth. And then you are somewhere above that height. And so this is giving you your R. But they're asking you for the altitude, which is kind of like that distance. So your altitude, in this case, would be your R minus the radius of the Earth. And so when you put these numbers in, make sure you're keeping your units consistent. So you want to have your R be in meters, and then when you subtract off the radius of the Earth, make sure that that is also in meters. All right, now I'm going to just say something a little bit puzzling. And it's that the gravitational potential energy that we use is negative. Now that might be puzzling to you because we've talked about how U is just mgh, but that's a sort of an approximation for when our gravitational potential energy is not changing very much, and we're in that regime where our gravitational force is approximately constant. So we're not changing our R very much in those types of problems. If we're going to change our R quite a bit, we need to start thinking a little bit more broadly. And so the gravitational energy is we think about this in terms of the amount of work it would take to disassemble a system. Now that might be a little confusing to think about, but think about it this way. Our Earth is going around the sun. The sun wobbles a little bit, the Earth wobbles a lot. Now if we wanted to take out our Earth and pull it off of the sun, you'd have to put in some work. Okay, how much work would you need to do? Well, work is force times distance. So force times, in this case, dr. And the force would have the shape of Newton's law of universal gravitation. So m1, m2 over r squared dr. And let's say we wanted to bring this thing out to infinity. Okay? How much work would I have to put in? Well, it would have to be, I can take the integral of this thing, and it would be minus gmm over r, not r squared. If you take the derivative of this, you'll get that. And we're going from r equals r to r equals infinity as my limits on my integral. And so there my work would be just minus, so it would be plus gmm over r. Now that's the amount of work that I would need to put in, but you want to think about the minus of that because you want to have some sort of energy conservation. And so this amount of energy is what you would need to put in to get up to 0. So if you put in this much energy, you get up to 0. And so 0 energy being those two objects completely removed from each other, not gravitationally interacting anymore. So the idea is that that negative energy, that's how much energy it has right now, because to get to 0, you'd need to pull apart, pull apart, pull apart. So that's the sort of the physics explanation for why you're assigning these negative energies to systems that are bound together. So like the solar system, you'd give it a negative gravitation. If you added up all the kinetic energy of the objects, or of the objects going around the sun, plus the gravitational potential energy, you get a negative number because these objects are bound together. On the other hand, if you took like a comet that's just whizzing by and it doesn't form a circle, that's called a hyperbolic or hyperbolic orbit, and it doesn't form an ellipse. It keeps on going by, and that's what happens if you have an overall energy that's positive. Now, the place we're going to use this is this. Let's say we want to shoot off a rocket from the Earth. Okay, so there's the mass of the Earth, and here's the mass of the rocket. And at the beginning, when I just shoot it off, my object has, the rocket itself has gravitational energy, and it has kinetic energy. And I want to have, so this is my start, and I want to have my finish such that my rocket is just, it's reached r equals infinity. It's gotten all the way out, and it continues to go out into the space, such that it's not being pulled on by the Earth anymore. And its V at that point is just 0. So here my energy, the total mechanical energy is 0. Now, this is the condition called, the escape velocity, because that's the velocity. If you just shoot off your rocket, you have 1/2 the minus gmm over r squared plus the kinetic energy of that object, 1/2 mv squared, equals 0. Now you'll notice the m's can be divided out on both sides with nothing lost, and then you can solve for v, which would give you 2g big M over r. So how fast you have to be going to shoot off of this planet depends on g, of course, the mass of the planet, and the radius that you begin your projectile motion going off. Now, this is a common thing to look at. Like, for instance, you look at the Earth. You can put in an r for the Earth. You can put in the mass of the Earth and calculate an escape velocity of the Earth of 11,186 meters per second. Okay, so v escape for the Earth is around 11 kilometers per second. Pretty fast. Of course, you might ask yourself, are the rockets that we shoot off of Cape Canaveral, are those NASA rockets going at 11 kilometers per second when we launch them? And the answer is no. And the reason why is that they continue to get to have momentum pushing out of the back and propelling them forward. That continues to go for a while. So it's not where you just spring load the rocket. The picture in this escape velocity is that you would have to spring load the rocket and just let it all go at once, and that would be the only energy that it would get. You wouldn't be burning a rocket at all. So you actually don't need to go quite this fast, but it is a good number to start thinking about how fast would you need to go to escape Earth. There's a little bit of subtlety there. All right, so that's our ideas for today. What have we gone over? Gravitational acceleration can vary slightly with elevation and local density fluctuations. So remember, g is gm over r squared. So the higher you go, the smaller your gravitational acceleration is going to be. In your book, if you're interested in this, they also have some interesting discussion about how your gravitational, your acceleration that you experience also depends a bit on where you are relative to the equator. So that's an interesting effect, but it's not a big effect. Okay, what else? Gravitational potential energy is considered to be negative, and if you have a negative total energy, that indicates that you have a system of bound particles. And then finally, the escape velocity from a planet or star is found by calculating where the sum of the total energy, the gravitational potential plus the kinetic, is equal to 0. Okay, so with that, we're officially done with our stuff in this unit. We have a homework due on Monday. You have a quiz to do right after you watch this video. And finally, we have a test 1 week from today. Okay, so a lot is going on. Thank you for watching, and have a great weekend.